In the previous lesson, we saw that the modern economy grows thanks to our trust in the future and to the willingness of capitalists to reinvest their profits in increasing production. Yet, that does not suffice. Economic growth also requires energy and raw materials. Without it, the economy cannot grow. And many people ask, what will happen when the energy sources and the raw materials run out? What will happen when there will be no more oil, or coal, or iron, or copper, and so forth? And this is something that is today central to arguments among the general public and economists and scientists. But the actual fact is that at least when we look back in history over the last 2 or 3 centuries, the danger of humanity running out of energy sources and raw materials is actually smaller than it seems at first sight. Because at least over the last 2 or 3 centuries, the amounts of available energy and raw materials just keep growing and growing instead of diminishing, as common sense would have us expect. What happens is that whenever there is a threat of shortage of either energy or raw materials, and this threatens to slow down the growth of the economy, investments begin to flow into scientific and technological research on the relevant subjects. And so far, the scientists and engineers, thanks to all this financial support, have always managed to solve the problem and to find more efficient ways of exploiting existing resources, or to discover completely new types of energy and of raw materials which previously we didn't know about. Consider, for example, the vehicle industry. Over the last 300 years, humankind has manufactured billions upon billions of vehicles, carts and wagons and trains and cars and motorcycles and airplanes and ships and space shuttles. One might have expected, this is common sense, that such a prodigious effort of building vehicles would exhaust our energy sources and the raw materials which are available for vehicle production, and that today, in the 21st century, we would have far fewer raw materials and energy sources to produce vehicles than in 1700. Yet, as everybody knows, just the opposite is the case. Whereas in 1700, the global vehicle industry relied overwhelmingly on wood and iron as raw materials to produce carts and wagons and ships. Today, it has at its disposal many completely new materials, such as plastic, rubber, aluminum, and titanium, which were simply unknown to our ancestors in 1700. Also, whereas in the 17th or 18th century, carts and wagons and ships were built mainly by the muscle power of carpenters and smiths. Most of the energy to build a ship came from the muscles of people and animals. Today, the machines in the factories of Toyota and Mercedes and Boeing that produce cars and airplanes and ships, they are powered not by the muscles of humans and animals, but by petroleum combustion engines and nuclear power stations, which of course did not exist 2 or 3 centuries ago. A similar revolution of having more and more energy and raw materials has swept almost all other fields of human industry and human production. And this revolution in production is called the Industrial Revolution. The most important thing to understand about the Industrial Revolution. The most important things that happened in the Industrial Revolution is not the discovery of this or that particular raw material or energy source, but the new understanding of humans that they are in fact surrounded by enormous, almost limitless quantities of energy and raw materials. And the main thing we really need to do is to find and invent ways to harness and control all this energy and raw materials. What is really lacking is not energy. What is lacking is ways to harness it. And every few years, or every few decades, scientists and engineers have indeed, over the last 2 centuries, managed to discover new sources of energy and new raw materials and new ways of harnessing them for our needs. The first really important breakthrough that began the Industrial Revolution occurred in British coal mines in the late 17th and early 18th century. During this period, the population of the island of Britain grew at a very fast rate, and forests were cut down in order to fuel the growing economy and to make room for houses and fields and villages and so forth. And therefore Britain began to suffer from a shortage of firewood. When people wanted to heat their houses in winter or to boil water to make soup or tea or whatever, they used firewood, and there was less and less firewood. So the British came up with a solution. They began to use coal instead. And more coal mines were opened in different parts of Britain to supply coal. But there was a problem. Many of the coal mines were located in waterlogged areas, areas with swamps and rivers and lots of water. And therefore, when the miners began to go more and more deeply into the mine, they suffered from flooding. And this prevented accessing the lower strata of the coal mines. To solve this problem, around the year 1700, engineers in British coal mines invented the steam engine, the first big invention of the Industrial Revolution. There are all kinds of steam engines, but they all work according to the following principle. You take some kind of fuel, you burn some kind of fuel like coal, and you use the resulting heat in order to boil water. When water boils, it turns into gas, into steam, and the steam expands. Now, as the steam expands, you use it to push a piston, and the steam pushes the piston moves, and anything that you connect to the piston moves along with it. The amazing thing about the steam engine is that it converts heat energy into movement. This is very counterintuitive. It's very easy to understand that I burn coal in order to boil soup or in order to heat my house in winter. But the idea that I can burn coal and by this I can move something, this is very counterintuitive, which is why it took thousands of years for people to think about it. But eventually they did, in Britain of around the year 1700. In the first steam engines, the piston, it was invented in the coal mines, as I said, so the piston was connected to a pump, and the pump extracted water from the bottom of the mines in order to prevent flooding. This was the first usage of the steam engine. But in the decades after its invention, British business people took the steam engine out of the coal mines into factories and began to connect the steam engines to all kinds of other things, like looms that wove cloth, that wove textile. And this was the real beginning of the Industrial Revolution, which very quickly turned Britain not only into the leading industrial nation of the world, but also into the leading economic and political power of the world. The next stage in the process came in 1825, when a British engineer had another great idea. If we can connect the piston to all kinds of textile machines in factories, why not use the same principle of burning coal to move things in order to start moving vehicles? And this engineer, he connected the steam engine to a wagon full of coal, and it drew the wagon along an iron rail some 20 kilometers long that connected the coal mine to the nearest harbor. And this was the first steam-powered locomotive in history. A mere 5 years later, on the 15th of September 1830, the first commercial railway line that moved not only coal but also all kinds of other goods and people was opened for business. It connected the city of Liverpool to the city of Manchester in Britain, two of the earliest centers of the Industrial Revolution. The trains connecting these two cities were propelled forward using the same steam power that was previously used in order to pump water and to move textile looms. 20 years later, in 1850, Britain already had tens of thousands of kilometers of railway tracks connecting all the major population centers and all the major cities. This invention of the steam engine was important not only in itself, but also because it broke a big psychological barrier. The steam engine proved that by inventing the right machine, you could use almost any kind of energy in the world for any purpose you want. You can use the energy from burning coal in order to move trains, which was, again, something very hard for people to grasp until the steam engine came and showed it how it can work. Once, however, people realized it, they began to invent all kinds of other machines that used various types of energy, not only heat energy, but all kinds of energies, to various types of purposes. For example, when in the late 19th century and early 20th century, physicists realized that immense amounts of energy are stored within matter, within atoms, in the connections that keep atoms together, they immediately started thinking about how they might harness this energy, release this energy, and harness it in order to produce electricity, in order to power vehicles, in order to win wars and annihilate cities. Only 40 years passed from the moment that Einstein determined that E equals mc square until the first atomic bombs obliterated the cities of Hiroshima and Nagasaki in Japan. E equals mc square, the big equation that Einstein discovered, what it means, E is energy and m is mass. It means that any mass of matter can be transformed, can be converted into immense amounts of energy. And this is what the atom bomb does. It releases the energy stored within matter, and in the case of atom bombs, uses it to destroy a city. But you can use this energy to other purposes. Today, we have nuclear power plants all over the world which provide us with cheap electricity, which we use to do all kinds of other things. Another crucial discovery of the last 2 centuries was the internal combustion engine, which took little more than a generation to completely revolutionize human transportation. It is the basis for all the cars and planes and so forth. And another thing that the internal combustion engine did was to turn petroleum into liquid political power, into a very important asset that countries fight over, petroleum, oil. Now, the funny thing is that petroleum had been known to humans for thousands of years. Even in ancient Mesopotamia, what is today Iraq, the Babylonians, the Assyrians, they knew about petroleum. They encountered petroleum, but they didn't do anything with it. They didn't know what could be done with petroleum. They used petroleum in order to waterproof ships and in order to lubricate axles. But that's about it. Until just a century ago, nobody thought that you could do much more with petroleum. The idea of fighting wars, of spilling blood for the sake of petroleum would have sounded ludicrous to Napoleon or Genghis Khan or Julius Caesar. You might fight a war, Napoleon or Julius Caesar would have thought, you might fight a war to get land. You might fight war to get gold or pepper or slaves, but to fight a war in order to get petroleum, this is ridiculous. Only in the last 100 to 150 years, people discovered that you can use petroleum to fuel cars and planes and so forth, and then they started fighting about it. Even more startling was the career of electricity. 2 centuries ago, in 1800, again, people knew about electricity, but it played no role in the economy. Electricity was used by scientists for all kinds of arcane experiments and by magicians to perform cheap magic tricks with electricity, which surprised everybody. But nobody knew what else to do with electricity. But over the last 2 centuries, a series of inventions turned electricity into a kind of universal genie in a lamp that do anything we want. We flick our little finger and electricity runs to the ends of the world to fulfill our every wish. Like here in the studio, all the lights are from electricity, the cameras, the computers, they all work with electricity. You watch this lesson on your computer thanks to electricity. If electricity falls down, it all stops. Hardly any of us really knows how electricity does all these things. I mean, physicists and electricians, they know, but most people don't know what electricity actually is and how it does all these amazing things. But hardly any of us can even imagine our lives without electricity. The Industrial Revolution was thus a revolution of energy. Its deep meaning is that there is no limit to the amount of energy at our disposal. Or more precisely, the only limit is set by our ignorance. Every few decades, we discover a new energy source as our knowledge becomes better and better. So the sum total of energy at the disposal of humankind keeps growing instead of shrinking. Hence, the common fears that we are running out of energy are probably exaggerated. The world does not lack energy. What it really lacks is the knowledge necessary to harness and to convert the existing energy to our needs. The amount of energy which is stored within all the fossil fuel on Earth, petroleum and coal and so forth, is negligible compared to the amount of energy that the sun releases every day, free of charge. Only a tiny portion of the energy released by the sun reaches planet Earth. But even this small bit amounts to 3,766,000 exajoules of energy each year. An exajoule is a very, very large quantity of energy. Now, all the plants in the world, on planet Earth, capture in the process of photosynthesis only about 3,000 of those millions of exajoules that reach Earth from the sun. All human activities and industries today on Earth, if you combine them together, consume in a year just 500 exajoules. This is equivalent to the amount of energy that planet Earth receives from the sun free of charge in just 90 minutes. And that's only solar energy. In addition, we are surrounded by enormous sources of other kinds of energy, such as, for example, by the nuclear energy in atoms and the gravitational energy, for example, the gravitational forces of the ocean tides. Prior to the Industrial Revolution, humans got almost all their energy from plants. Almost everything humans did was fueled by eating plants themselves to fuel our muscles, our feet, our hands, by feeding plants to our work animals like horses or donkeys, or by burning plants such as wood in order to heat houses and cook things and things like that. This meant that throughout most of history, humans, everything they did was based just on exploiting these 3,000 exajoules of energy that plants capture every year from solar energy in the process of photosynthesis. During the Industrial Revolution, we humans came to realize that there is actually much more energy out there. There's not just the 3,000 exajoules in plants. There are millions and millions of exajoules of potential energy which we can use if we can only invent better machines to harness all that energy. So this is energy. This is the problem of energy. Now, what about raw materials? Okay, we have lots of energy around us, but aren't raw materials such as iron and copper and so forth, aren't they scarce? Won't they eventually just be completely used up and we'll have nothing more to use? Well, the answer is that once you know how to harness large quantities of cheap energy, once you solve the problem of energy, you can also solve the problem of raw materials. Because, for example, if you have a lot of cheap energy, you can exploit previously inaccessible deposits of raw materials. If you don't have any more iron in easily accessible mines, say in Sweden, you can start mining iron in the North Pole. It's not easy, but if you have all the energy in the world you want, so it's not impossible either. Another thing that you can do if you have a lot of energy is to transport raw materials from more and more distant locations. In the 19th century, for example, British textile manufacturers, they needed more and more wool. The wool in Britain itself and Ireland and Spain was not enough, so they began importing wool from Australia and New Zealand. Now, previously it would have been impossible to import wool all the way from Australia because of the cost of transporting the wool from Australia to Britain. But with the invention of steam engines and ships that work with steam, it became cheaper and more economic to bring wool from Australia to Britain. And today, when people are looking for new sources of raw materials, they say, why not take iron and copper and aluminum and so forth from the moon or from the stars or from asteroids? If we have a lot of cheap energy, the cost of transporting it to Earth would not impede even such grandiose plans. Simultaneously, scientific breakthrough also enabled humankind to simply invent completely new types of raw materials that didn't exist before, such as plastic or to discover natural materials that always existed but people knew nothing about, such as silicon and aluminum. Chemists discovered the metal aluminum only in the 1820s. Previously, they didn't know about it. But separating aluminum from its ore was extremely difficult and costly. Therefore, for many decades, aluminum, even though people knew about it, it was more expensive than gold, because it cost a lot of money to take ore and extract from it aluminum. In the 1860s, the Emperor of France, Napoleon III, the nephew of the famous Napoleon, he commissioned aluminum cutlery, forks and knives and plates, to use when very distinguished guests are coming for a visit. If the Prime Minister of Britain or the Queen of England come for a visit, they take the gold plates and gold forks and knives and put them aside and serve the food in aluminum cutlery, which is much more luxurious and much more expensive. But at the end of the 19th century, chemists discovered ways to extract immense amounts of aluminum very, very cheaply. And today, the world produces 30 million tons of aluminum each year. So Napoleon III would be very surprised to hear that today we think that aluminum is something very cheap, and we use aluminum paper to wrap our sandwiches and then throw them to the garbage. Another interesting case of discovering a new and cheap way of extracting raw materials involved what happened in Germany in the First World War. During the First World War, Germany was placed under blockade, and it suffered from severe shortages of all kinds of raw materials, and particularly severe was the shortage in saltpeter. Saltpeter is some kind of chemical that is essential for producing gunpowder and other explosives. The most important saltpeter natural deposits of saltpeter in the world were in Chile and India. And in Germany itself, there are no natural deposits of saltpeter. Now, by the early 20th century, chemists knew that you could replace saltpeter in the production of explosives by synthetic ammonia. But ammonia, it was extremely expensive to produce ammonia, so it was not really a solution. And this was a very big problem because during war, the First World War, you need to produce a lot of explosives. Luckily for the Germans, there was a Jewish German chemist called Fritz Haber. And in 1908, just before the war, Fritz Haber discovered a process for producing ammonia from thin air. You just take air, normal air, like the air here in the room, and you can, in some kind of chemical process, bind the nitrogen atoms from the air and produce ammonia. And you can then use this ammonia for explosive and other things. And when the war erupted, and the Germans faced this crisis of there is no saltpeter to produce explosive and gunpowder, they poured resources, they poured money to develop this new discovery of the chemist Fritz Haber, and they built huge factories which produced explosive ammonia and explosive simply from air. And many historians, many scholars believe that if it wasn't for the discovery of Fritz Haber, Germany would have been forced to surrender long before November 1918 because it would have run out of explosives. This discovery, by the way, won Fritz Haber the Nobel Prize in the year 1918. Not for peace, of course, the Nobel Prize for chemistry. The Industrial Revolution thus gave people not only cheap and abundant energy, but also cheap and abundant raw materials, and we have more and more of them with each passing decade. And the result was an explosion in human productivity. You take a lot of energy, a lot of raw materials, you combine them, you get a lot of productivity. How this explosion of productivity affected humans and also other animals will be discussed in the next segment of this lesson.